Hi. Now in this video we'll see how we can use the limit or the definition of a limit to prove some theorems. In particular we want to prove the following theorem. Right, so if the limit as x tends to f of x is L, and the limit of g of x as x tends to is m, then the limit of f of x plus g of x as x tends to a is L plus m. Right. So let's just remind ourselves quickly what we have to prove. Right. Now this is not part of our proof, this is what we want to prove. Right. Required to prove. For any positive number delta, for every positive number epsilon, there exists a number delta bigger than 0, so that if absolute value x minus a is between 0 and delta, then absolute value f of x plus g of x minus L plus m is less than epsilon. Right, so this is what we want to prove. Yeah. So now let's look at the actual proof. Right, so the first step is always to see, well, what is it that I have to prove? Right, and the second step is to see, well, what do I know? What do I know that can help me? Well, as we do when we try to evaluate a limit using the definition, as in the previous videos, we start off with this. We want this to be less than epsilon. Right. And let's see. Well, f of x plus g of x minus L plus m, we can write that as absolute value f of x minus L plus g of x minus m. And now we use the triangle inequality to get this is less than absolute value f of x minus L plus g of x minus m. Right, and let's call this inequality A. Right, now why would we want to do this? Well, these two terms we can control, right, because they're involved in the definition of a limit for these two limits. Right, so we can take care of them. Right. So now let's see, what else do we know? Well, we know that the limit as x tends to a of f of x is L. Right. And we know, so that means that for any epsilon bigger than 0, there is, say, delta 0 bigger than 0, so that the following holds. Absolute value x minus L is between 0 and delta, then absolute value f of x minus L is less than epsilon over 2. Now why epsilon over 2? Well, if this is less than epsilon over 2, and that is less than epsilon over 2, then the whole thing is less than epsilon, which is what we want. Right. But we also know that the limit as x tends to a of g of x is m. Right? Now that means that for epsilon bigger than 0, we can find, say, delta 1 bigger than 0, such that if absolute value x minus a is between 0 and delta 1, then absolute value g of x minus m is less than epsilon. Right. So let's call this whole thing, say, B, and this whole thing we call C. Sorry. We must have it less than epsilon over 2. Right. So now we want this to be less than epsilon over 2 and that to be less than epsilon over 2 at the same time. Right, so for the same values of x, both these terms must be less than epsilon over 2. Right. So now for f we have a delta and for g we have to have a delta. Right, so now we need to find one delta that will work both for f and g. Right. And so now if we take epsilon bigger than 0, let delta be the minimum of delta 1 and delta 2. Right. So it is small, that's delta 0 and delta 1. Right. So this delta is less than that delta 0 and less than delta 1. So if absolute value x minus a between 0 and delta, then by b and c, well, f of x minus l is less than epsilon over 2 and absolute value g of x minus m is less than epsilon over 2. Right, so both inequalities are true. Right. So then our first inequality A, right, this one implies that absolute value f of x plus g of x minus l plus m is less than epsilon over 2 plus epsilon over 2, which equals epsilon. Right. So this is true for all epsilon bigger than 0. So by the definition of the limit as x goes to a, f of x plus g of x is l plus m. Right. And that's how this theorem is proved. So it's important to note again, right, that when you're proving something, it's a logical argument. Right. The words we write here, they're also important. Right. They give meaning to the symbols. And we have to clearly indicate where we use our assumptions. Right. So here we've indicated that from the assumption that the limit of f is L, we get this. And here we've indicated that from the assumption that the limit of g is m, we get this. Right. And here we've indicated clearly when we've used things we've done previously. Right. And that's important. That's part of a proof. Right. A proof is a logical argument, right, which is well motivated and clearly written. Right. And we clearly show how we connect the assumptions to the conclusion. In other words, where we use the things we assume in the theorem. Right, these are the assumptions. And this here, that's the conclusion. Right, and we have to clearly show how we use the assumptions to show that the conclusion is true. Okay.